Skillshare is an online learning community that offers thousands of inspiring classes for creative and curious people on topics including illustration, design, photography, web design, freelancing, and more. We're already mostly just sitting at home and watching online classes, so why not learn something tangible and develop your creative side? There's so many lessons on painting, productivity, web development, and a whole slew of other topics that you can't really go wrong with Skillshare. This series on productivity, for example, by fellow future attending physician Ali Abdal, is quite good when you're stuck in a productivity rut. And best of all, Skillshare is quite reasonably priced for us debt-ridden college students. It's less than $10 a month for an annual subscription. And if that sounds good, there's an additional kicker. Because Skillshare is sponsoring the video, the first 1,000 people to use the link in my description will get a free trial of Skillshare Premium membership, so click the link in that description and make this year a productive one.
Are you tired of being called a scrub because you only know how to solve second-order partial differential equations? Worry no more, because in this video I'm going to teach you how to solve a fourth-order PDE so you can show people that you're a real Chad. Anyway, welcome to another video on partial differential equations. Staying on the theme of wave equations, this video is going to solve a special kind of wave equation that doesn't really take the form of a wave equation that you're used to. It's the equation of the quote-unquote waves that occur on a solid vibrating beam. You might recall the wave equation on the string as the second partial of u with respect to t is equal to the speed of the wave c squared times the second partial of u with respect to x. The quote-unquote wave equation on a vibrating beam is slightly different from the regular wave equation on a string. Because the beam's much more rigid, the equation of vibrations on a beam becomes a fourth-order partial differential equation. In this video, I won't actually derive this PDE since that's beyond the scope of our PDE lessons. The alpha, by the way, is the constant related to the rigidity and mass per unit length or linear density of the beam. Let's draw a beam to illustrate this PDE a bit better. So here's a beam between 0 and L. U represents the vertical displacement of the beam with respect to the horizontal axis or the x-axis. In general, this u is both a function of position along the horizontal axis x and the time t. Additionally, the alpha squared equals the Young modulus E times the area moment of inertia I. But remember that whenever we talk about a moment of inertia, we must specify the axis we're calculating it with respect to. In this case, we calculate this area moment of inertia with respect to the x-axis. This EI quantity, by the way, is called the flexural rigidity. Finally, we have a mu dividing the flexural rigidity, and this mu represents the mass per unit length of the beam, or the linear density. Anyway, now that we've fully described the meaning of the variables in this PDE, let's actually solve this fourth-order partial differential equation for the case of a simply supported beam. Now let me draw a simply supported beam to show you what it looks like. So here's a beam again of length L, and when I say it's simply supported, I mean that it's a beam that's fixed at two ends such that u is 0 at both x equals 0 and at x equals L. It's fastened at the two ends. So these boundary conditions should be obvious from the fact that the beam is fastened at the two ends. The other important boundary conditions that arise from this problem are the boundary conditions on the second partial of u with respect to x. This second partial of u with respect to x is related to the bending moment of the beam. And using arguments from beam mechanics, you can show that the bending moment of the beam must be 0 at both ends if the beam is simply supported like in our example over here. I won't demonstrate those arguments here since this isn't a video on beam mechanics. For the purposes of this lecture, it's probably sufficient to just accept my arguments at face value since it's really about how to solve this fourth-order PDE. Finally, in addition to the boundary conditions on this beam, we also have initial conditions. Since the PDE is second order in time, we must have two initial conditions, one on u itself and the other on the first partial of u with respect to time. Both these initial conditions are equal to some arbitrary function of x, u0 for the u initial condition and v0 for the partial u partial t initial condition. So if we put all this together, here's what our PDE problem looks like for the simply supported vibrating beam. I've got a fourth-order PDE governing the oscillations of a thin vibrating beam, 4 boundary conditions because the PDE is fourth order in x, and 2 initial conditions because the PDE is second order in time. Now look at the problem we have here. We've got a fourth order homogeneous PDE because all the terms either involve u or its partial derivatives. There's no non-u term being added that's a function of x or t. In addition, the boundary conditions are also homogeneous. They're all equal to 0. And if the PDE and boundary conditions are all homogeneous, how do we solve the problem? Well, if you've watched my previous videos, then you'll know that the standard way to solve such problems is to use separation of variables. Recall that in separation of variables, we assume that the solution u is composed of a function of x only multiplied by a function of t only. If we take the second partial of this with respect to t, we'll get capital X times the second derivative of capital T with respect to time. This is because capital X is a constant with respect to time, so when we take the second partial of u with respect to t, we only have to focus on the capital T as a function of time, since the capital X is just a constant as far as this partial derivative in time is concerned. In addition, if we take the fourth partial of u with respect to x, we'll get capital T times the fourth derivative of capital X with respect to small x. This time, capital T is just a function of time, so we only have to focus on capital X, since capital T is a constant as far as the partial derivative in x is concerned. Let's plug these two partial derivatives into the PDE, and if we do that, this is what we get. The next thing we'll do is separate the variables x and t, so we'll divide both sides by u, or capital X times capital T. Now the left side is only a function of the time small t, while the right side is only a function of the position small x. So if I change time, then my capital T, which is a function of time, could change, and the derivative of capital T, also a function of time, could change as well. However, changing time doesn't change anything on the right-hand side because there's nothing there which is time-dependent. So even though the individual terms on the left might change, their combination doesn't change because the combination has to equal the right-hand side, which is constant with time. Similarly, if I change the position x, then the left side of the equation stays constant, which means that the right side must also remain constant. So changing either x or t doesn't affect either half of the equation, so we say that both halves must be constant. You can also prove this to yourself by taking the derivatives of both sides with respect to small x and small t to show that the whole equation actually does equal a constant. The problem now is that we don't know what this constant is. Specifically, do we pick a negative constant, a positive constant, or a zero constant? I'm going to actually show you using the process of elimination that the constant is negative. Let's look at the differential equation for t, for small t, to demonstrate this. If the constant is positive, I can write it as the square of a non-zero real number omega. A real number square is always positive, so omega squared is always going to be positive. If I solve this ODE, I'll get the sum of two exponential functions, a decaying exponential and a rising exponential. The rising exponential is clearly an unphysical solution. The waves can't keep getting bigger and bigger with time without bound. However, the decaying exponential is also unphysical. Remember that a wave equation like this is supposed to oscillate with time. In the absence of any friction terms, it's unphysical for the wave to just fizzle out. It has to oscillate, so the constant can't be positive because both components of that solution are unphysical. Now, what if the constant is 0, in which case my ODE for time becomes the following. The solution to this ODE is just a line. This line is also an unphysical solution. The wave can't just linearly increase or decrease with time. That's not possible with a wave. A wave has to oscillate, so the constant can't be 0 either. That just leaves the case that the constant is negative. In that situation, we can write the constant as negative omega squared, where omega is a non-zero real number. And when you solve this ODE, you'll find that capital T is the sum of a sine function and a cosine function. And note here that a and b are both integration constants. But we haven't fully solved the PDE yet. We still need to solve the capital X equation. For a negative omega squared constant, the X equation looks something like this. Let's take the coefficient of the fourth derivative and move it to the other side, and then move the term on the right to the left so that I get a differential equation that equals 0. So now we've got to solve a fourth order ordinary differential equation with constant coefficients, And the way to solve any linear ODE with constant coefficients is to assume the solution carries the form e to the rx, where r is some number that you have to solve for. If we plug this into the ODE, you'll find that the fourth derivative term has an r to the 4 in front of it, because every time we differentiate e to the rx, we get the r to come out and multiply the whole thing, while the exponential stays as the exponential. Meanwhile, the simple capital X we already know is e to the rx. Now we can cancel the e to the rx because it can never be 0, in which case we get the following equation for r. I'm going to define another constant beta as omega over alpha just to simplify the writing a bit. When I do that, I get r to the 4 minus beta squared equals 0 as my equation for r. We can then factor the left-hand side of this equation into r squared minus beta times r squared plus beta equals 0. The r squared minus beta further factors to r plus the square root of beta times r minus the square root of beta, while the r squared plus beta factors to r plus I times the square root of beta times r minus I times the square root of beta, where I is the imaginary number, I squared equals -1. So in the end, we end up with these 4 roots for r, given by setting each of these factored terms to 0. So the overall solution for x is obtained from taking a linear combination of these corresponding exponentials. When we do that, here's what we get. Now I can use any linear combination of these exponential solutions, and that would still work as a valid solution. So I can take 2 different linear combinations of these real exponentials to get 2 hyperbolic trigonometry solutions, hyperbolic sine and hyperbolic cosine. In addition, since the imaginary exponentials are directly related to sine and cosine, we can take the appropriate linear combinations of these imaginary exponentials to give us 2 other solutions, the simple sine and the simple cosine. So at this point, we've got our capital X and capital T. Our u would then just be the product of these two and would be given by the following, where again the constant beta is defined as omega over alpha. Anyway, I'm going to stop here because if I fully solve this PDE problem, I'm going to go over the 50-minute video limit that I set for myself. In the next lesson, we're going to apply the initial conditions and boundary conditions to determine these constants a through f. I'd like to thank the following patrons for supporting me at the $5 level or higher, and if you enjoyed the video, feel free to like and subscribe. This is the Faculty of Khan signing out.